everyone. Welcome to the lecture on Chapter 3, Section 1, Coordinate Systems. So this is from Chapter 3, which is on vectors. So let's just jump right into this here. Let me grab an axis first. Let's grab an XY axis. So this is kind of what we're used to seeing from our math studies, right? So we have our X and Y axes here and here. Whoa, man, I'm all over the place right now. All right, X and Y, and we can put points on this, right? We have X1, comma Y1 over here. Maybe we have another point down here. X2, comma Y2. But either way, make this a little bit thicker. Maybe that'll help. Either way, this is kind of what we've been used to doing. A little dot over here. So in our algebra, calculus, whatever math, even geometry, whatever you're up to. This is our Cartesian coordinate plane, right? This is how we've been used to dealing with things up until now. If you've taken some other math classes, you may have gotten into polar coordinates. But that's kind of what we're going to be talking about today. Basically, another way to define these points. So it's going to define the same points. So x1, point 1, point 2, and point 3. Point 1, point 2. Point 3. We're still going to be defining those in the exact same locations they are. We're just going to be defining them by using a different technique. Instead of using this xy, we're going to define these points by the distance they are from the origin. That is not a straight line, but hopefully you get the idea. So that's our r, right? Our radius, our radial distance from the origin to the point, and also by a tangent, or excuse me, a angle, theta. That's a terrible theta. So instead of distance to the right or left and distance up or down, which is what x and y tells us, we're going to have a distance, a straightaway distance from the origin, a radial distance from the origin, and an angle theta. You end up in the exact same spot. It's just a different way to define those. Obviously, what we need to do is we're going to be dealing with some Cartesian planes. We're going to want to move them to polar and so on and so forth. And we're just going to use some basic trig to do this. Right? We know that x1, y1 is a measure. This measurement here is y1. And this measurement down here is x1, right? That's how planes work. So what we have is we have a triangle. Man, my lines are not straight today. Actually, let's do this again. Oh. There we go. There we go. I knew I could do straight lines. But now this last one's not going to be straight because, yeah. Good enough. So there's our triangle, right? And then what we talked about here is we have this measurement theta and this measurement r, and we have this measurement as our x measurement. I should really change the thickness of that line, and this measurement as our y values, right? So this is what we have. We have a triangle, r, x, y, and theta. We have 4 measurements. So we can find these. We can pretty much find what r and theta are by our basic trig values. So we know that the sine of theta is equal to opposite over hypotenuse, right? O over h. That looks a lot like a theta there. O over h, which in this case, our opposite is our y value, and our hypotenuse is our r value. And same thing, we can use our cosine theta value. My tablet's not working that great today, which is going to be x. Oh, I got a little ahead of myself. Our cosine theta value is adjacent over hypotenuse, which would be x over r, right? And then finally, we also have tangent, which will come in handy for finding our actual theta value, right? Theta is opposite over adjacent, which in this case is going to be y over x. So using these equations, we'll basically be able to figure out everything we need. The other non-trigonometric equation, but more of an algebraic equation we'll also use our Pythagorean theorem, which is going to be r squared is equal to x squared plus y squared to find the magnitude of r. So pretty much using these 4 equations, here I'll even move this down. Using these 4 equations, we'll be able to translate from polar to Cartesian and Cartesian to polar. Pretty much that's what you need to know. A quick example of that would be on page 54 of your textbook. Let me grab a snapshot here. So, the Cartesian point on an xy plane is x equals negative 3.5, y equals 2.5, blah, 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 blah. So here, let's, I know they do give us the, yeah, I know. They do give us a picture of it, but let's draw it out ourselves just to get in the habit of doing so. Over there. And then always label your axes, super important. All right, x. Let's put your little arrows there. Even my arrows are not very straight, and this is y. So let's see. We have a point here. It's negative 3.5, negative 2.5. I'm just gonna eyeball this. I'm not super concerned with my scale right now, but we know we're at negative 3.5. I know it's sig figs, blah blah blah. We're just trying to figure out how to do this for now. So, and they want us to find the polar coordinates at this point. So they want us to draft this up in terms of, there we go. Now I'm getting better with straight lines here. R, and then our angle theta is always measured from, whoa, I didn't know I could do that. Didn't mean to do that. Our angle theta is always going to be measured from the positive x-axis around in a circle. So 90, you have 90, 180, 270, then back to 360. If you go the other way, it would be negative. So the down y-axis would be negative 90. But in this case, this is what we're looking for. So we're looking for this r value and this theta value. So if we slide over here a little bit, come on, you can do it. There we go. Slide over here a little bit and get cracking on this. So the easiest one, I mean, it's just going to be, like I said, we'll even draw our little triangle out. We'll draw it in the correct direction as well. So we have a line there, and a line there. So this is what our triangle looks like. Trying to be consistent with my colors here. So we have an angle theta, we have a dimension r, and then we have our given x and y values. So I'm just going to put the values in here. So 2.5 and 3.5. I'm not putting the negatives because I'm just worried about the geometry right now. I'm not actually worried about where it is in space. I'm just trying to do some calculations here. Your r value is pretty much always going to be positive. A negative r value would mean it's in the opposite direction. So like this blue r value we have here, if it were negative, it would be going up like this. That would be the negative version of that. But we're not going to have to deal with that very often. Erase that real quick. All right. So if we want to find this, like I said, just start off for the magnitude of r, Pythagorean theorem it up. So r is going to be equal to the square root of 2.5 squared plus 3.5 squared. And that's just some math. And you end up coming up with, let's see what we get here, 4.3. And this is in meters, right? Because this is all, yep, meters. So our radius is going to be 4.3 meters, and then scroll down a little bit to come up with the angle. Like I said, in most cases, you're going to use tangent just because you're usually given x and y. Now that we have the radius, technically we could use any trig identity or any of our trig functions, sine, cosine, or tangent. But since we were given x and y, we calculated r, let's say by some terrible mistake, we made a mistake calculating our r value, got the wrong value. Then if you go back and use that r value to calculate your theta, you're going to get your wrong theta too. So it's always a good idea to use what was given whenever you can, as opposed to using something you calculated. Just not a huge deal. In most cases, you're going to be getting it right, but just in case you're not, you always want to check that. So I'm going to say theta is going to be equal to the inverse tan or the arctan of my y over my x. So in this case, it's going to be 2.5 over 3.5. And that comes out to be, when you run that calc, always make sure you're in the correct mode. So generally, mathematically, we're going to be in radians. In most physics classes, though, we're going to be dealing with degrees. There will be cases where you're doing radians, so just when you're using your calculator or whatever calculator you're using, online calculator or whatever, just make sure you're in radians or degrees. It's a real easy mistake to make. So this comes out to be 216.